For the next group of questions, 12 to 15, we're using this definition of continuity. And for the given function and the given c value, we want to state which one of these conditions are true. All right, the first function is a polynomial. Now we know, remember that polynomials are continuous everywhere. Certainly f of c exists. A is true. Certainly the limit exists, you just substitute in. And the two are equal. Okay. So A, B, and C are true for polynomials. All right, let's look at this rational function. And this, the value that we're looking at is c equals 3. c equal 3 does not make the denominator 0. c equal 2 would be a problem, not c equal 3. So A is no problem. F of 3 is equal to 3 minus 5 minus 2 over 1. B also, we take the limit by simply substituting in. The limit as x goes to 3 is again minus 2. And the two are equal. A and B are equal, so C is true. Number 14, we're doing the limit as x goes to 1. Now notice, if we substitute in 1, the denominator is 0. So for that reason, f of 1 does not exist. So A is not true, so the function is discontinuous. So what about B? Well, we want the limit as x goes to 1 of this quotient, and I'm going to factor the numerator right away. Because when we factor this difference of 2 cubes, and we use that difference of 2 cube formula, we get x minus 1 times x squared plus x plus 1. So we have an x minus 1 in the denominator that cancels with the x minus 1 in the numerator. So at this point, after canceling, we can substitute in x equal 1, and we get 1 plus 1 plus 1, we get 3. So the limit does exist. B is true, but C is not true because these two aren't equal. This one does not exist, so certainly they can't be equal. Okay, let's look at number 15. We have a piecewise defined function. Let's start with condition A. Does f of 3 exist? Well, yes, we substitute into the bottom line because of this greater than or equal to figure out what f of 3 is. F of 3 is equal to 3 plus 1. F of 3 is 4. All right, let's look at B. So A is true. Let's look at B. We want the limit. Well, first of all, the limit as x goes to 3 from the left, we would substitute into the top line. And we have 5 times 3, 15 minus 3. We have 12. And let's do the limit as x goes to 3 from the left, from the right. Substitute into the bottom line. And we have 3 plus 1, 4. So these are not equal. That means the limit does not exist, so B is not true. Okay, so certainly C is not true as well, because the this limit certainly can't equal 4. It doesn't exist. In number 16, we want to find the one-sided infinite limit. Now this is an infinite limit because if we substitute in 4, we get 0 in the denominator, and that doesn't cancel with anything in the numerator. In other words, there must be an x minus 4 in that denominator. In fact, let's factor the denominator. Okay, factors into x minus 4 times x plus 3. Just check that out. Check the middle term. Minus 4x plus 3x is minus x. So 4 does make the denominator 0. So that, and it does not cancel with an x minus 4 in the numerator. So that means that the quotient is going to tend towards either infinity or minus infinity. So that's what we have to do, just figure out, is it infinity or is it minus infinity? So all we have to do really is do a little plus minus analysis of the quotient. Okay, that's our quotient. On the number line, we put zeros of numerator and denominator. So we're going to put 0 here. We're going to put minus 3. I use open circles for the denominator zeros and closed circle for the numerator 0. And we're going to put in 4, open circle. We want the limit as x goes to 4 from the left, so that's here. So this is the interval we're interested in. Just take a value between 0 and 4 and substitute in and see if you have something positive or negative. All right, so let's say we substitute in a 1, for example. Numerator is positive. X minus 4 will be negative. 1 minus 4 is negative. 1 plus 3 is positive. So we have 1 negative. That makes this negative. So the limit, that means, is minus infinity. Okay, number 17. Let's first factor that denominator. We want to take the limit as x goes to 2 from the right, and we see that the denominator tends to 0, which means that this quotient tends to either infinity or minus infinity, since the x minus 2 does not cancel with anything in the numerator. We do the same that we did in the previous example. We do a little plus minus analysis. Putting zeros of numerator and denominator on the number line. So we put x equals 0 for the numerator, and then we have 2 and 3. 2 and 3. We're interested in the limit as x goes to 2 from the right. So we have to substitute in a value between 2 and 3. Let's say 2.5. All right, we substitute in 2.5 here. That factor is positive. Here we have a negative, and here we have positive. So 1 negative, the rest positive, that would be negative. And again, this quotient tends to minus infinity as x goes to 2. In number 18, we have this function that's a quotient, and we want to find the discontinuities. So the first thing that we do is we factor numerator and denominator, especially the denominator, for finding discontinuities. It's a rational function, so the discontinuities occur at the zeros of the denominator. So just by looking at the denominator, we see discontinuous at x equal minus 5. That's the 0 of x plus 5. And x equal 2. Now what about the limit as x goes to minus 5? Well, the denominator is going to infinity or minus infinity, depending on which side we're on, which side of minus 5. So b is not true. The limit as x goes to minus 5 is infinite. Let's say it's going to be either positive infinity or minus infinity. The limit as x goes to 5 from the right is definitely infinite, either positive or minus. So that means that the limit doesn't exist. So non-removable at x equal minus 5. So we have discontinuous at x equal minus 5 and non-removable at x equal minus 5. How about as x goes to 2? The limit as x goes to 2 Well, we can cancel out the x plus 2 top and bottom. And we get the limit as x goes to 2 of x plus 2 over x plus 5. And now we have no problem substituting in x equal 2. So that would be 4 over 7. So the limit as x goes to 2 exists. So that is removable at x equal 2. All right, just to write this a little neater, at x equal minus 5, we have discontinuous, non-removable, and at x equal 2, we have discontinuous and removable. Again, removable at x equal 2 simply because when we take the limit, we can cancel out x minus 2 top and bottom and substitute in, so the limit does exist. In number 19, we're asked to prove that this function has a 0 in the interval minus 3, 2. That means it's equal to 0 for some value between minus 3 and 2. So we're going to apply the intermediate value theorem. And if we can show that the function is negative at one endpoint and positive at the other, that is, let's call this function f of x, say. We're going to look at f of 3 and f of 2. If one value is positive and one value is negative, that means that 0 is in between. So then that's a perfect situation for using the intermediate value theorem. All right, so first, before we use the intermediate value theorem, we need a function that's continuous. So our first line, and this is always the first line in these problems that involve the intermediate value theorem, our first line is f of x is a polynomial, therefore it's continuous everywhere. We just write polynomial, therefore continuous. Okay, and then we check the value of the function at minus 3 and the value at 2 and see if 0 is in between these two values. Because if a function has a 0 in the interval, that means that for some c here, f of c is equal to 0. That's what it means to have a 0 in the interval. All right, so let's look at f of minus 3. Cube f of minus 3, and we get negative 27. I'm just plugging minus 3 here into here. Minus 2 times minus 3 plus 5. That's negative 27 plus 6 plus 5. So that's minus 16. All right, so f of minus 3 is negative. Let's look at f of 2. Substitute into x cubed, we have 8 minus 2 times 2 plus 5. 8 minus 4 plus 5, that's 4 plus 5, that's 9. So this is negative, this is positive, and 0 is in between. Okay, so that's all we have to indicate. 0 is in between minus 16 and 9, so we could say that therefore, c exists. That is, this c, such that f of c is equal to 0 between minus 3 and 2. Now, we're not told to find c. Sometimes we are, but in this case, we're just proving that c exists without actually finding it. In number 20, we have f of x equal to x squared minus 4x plus 5. We want to show that f of c is equal to 2 in the interval 2, 5. So we have to show that there is a c between 2 and 5, such that f of c is equal to 2. We'll start with the intermediate value theorem, so we'll say we have to, before we use the intermediate value theorem, we have to say that our function is continuous. So in this case, f of x is a polynomial, so it's continuous. let me add something to the previous problem. Here we say 0 is between minus 16 and 9, so therefore you should mention by intermediate value theorem, IVT. By intermediate value theorem, C exists. Don't forget to mention the intermediate value theorem. All right, so here we won't forget it in number 20. First, to use the intermediate value theorem, we say f of x a poly, so it's continuous. And now we check the value of f at 2 and the value at 5. And we want to see if this 2 fits in between. So f of 2, let's see, that's x squared, that's 4, minus 4 times 2 is 8, plus 5, so that's minus 4 plus 5, that's 1. Now let's substitute in 5 here. We get x squared, 5 squared, that's 25, minus 4 times 5, that's minus 20, plus 5. So here we have 5 plus 5, that's 10. Yes, 2 is in between. Okay, so because of this situation, therefore, by intermediate value theorem, C exists. Now here we are asked to find the value of C. So in other words, for what value of x is this equal to 2? So we're just going to set this equal to 2 and solve. All right, so here we have f of x set equal to 2, and we just have to solve for x. Subtract 2 from both sides. First, let's see if we can solve this by factoring. If not, we'll use the quadratic formula. Yes, this does factor x minus 3, x minus 1 equals 0. So we have two solutions, x equals 3, x equals 1. We're looking for the solution in the interval 2, 5. So this is the one we're looking for. Okay, so 3 is in the interval 2, 5. So C is equal to 3. In number 21, we want to find the vertical asymptotes. The vertical asymptotes are zeros of the denominator after reducing. Okay, so if you have a rational function like this, the vertical asymptotes are at zeros of denominator after reducing. Okay, so let's see, what is f of x equal to? We're going to just see if we can reduce this. So we see an x can be factored out of the denominator. Let's do that first. And now let's see if this denominator could be factored further. It doesn't look like it could be factored. All right, I don't see how to factor this. So let's see if there's some solutions that we can get from the quadratic formula. We'll just check b squared minus 4ac. If it's negative, we know that this does not give us any zeros, or no place where this is equal to 0, no real number. So the only vertical asymptote in that case will be coming from this, will be x equals 0. So let's do b squared minus 4ac, and that's what's underneath the square root of the quadratic formula, the discriminant, and see if it's negative. All right, so b squared, that's 1 squared, minus 4ac. Okay, yes, definitely negative. Okay, minus 159. Negative. Imply no roots or no zeros. So the only vertical asymptote is at x equals 0, coming from this. In 22, we want the slope of the secant line from x equals 2 to x equals 3. So let's call this x value a and this x value b. And the slope of the secant line is equal to the change in the y values. That would be f of b minus f of a divided by the change in the x values. Using our notation, that would just be b minus a. So f of b, that's f of 2 minus f of 3. Sorry, f of b is 3. F of 3. And a is 2. F of a, that's f of 2. Over 3 minus 2. So let's just do f of 3 here on the side. Substituting in here, we have 9 minus 2 times 3 minus 6 plus 5, that's 8. And let's look at f of 2. F of 2, that's 2 squared, that's 4, minus 4, plus 5, that's 5. Okay, so this is equal to 8 minus 5 over 3 minus 2. That's 3 over 1.